This is a slightly edited version of the talk I've given at the OOP conference in Munich on the 4th of July. In the beginning, I'm a bit nervous as it has been a good 5 years since I've talked to actual people in the same room with me. Please enjoy.
Okay. Thank you. Sind doch ein bisschen mehr geworden, als ich gedacht habe. Genau, mein Thema ist, ob Clean Code funktioniert. And I switch language. My topic is going to be about clean code, whether I think it works or not. As a quick spoiler, my personal opinion is that it doesn't work. Well, it works in the sense that you will get a code out of it that does function, but it doesn't achieve the points it's trying to set out. That's more the point. And I have to start with a couple of disclaimers. First of all, I'm talking about Clean Code, the book and concept, not Uncle Bob or Martin C. Robert C. Martin, sorry. As a person, I'm not interested in him as a person or his political viewpoints or morals. It's not the subject. I'm interested in his arguments. Next thing is I'm leaning towards the functional side, so I have, of course, obvious biases concerning this. And the third thing is, this is my opinion. Materna left me complete freedom about what to talk about. It doesn't necessarily represent their viewpoints. It doesn't necessarily not represent their viewpoints. I didn't check, so that's that. Those are the sorry. Been told that I should always start with a comic. I picked this one specifically because Clean Code starts with the same one, a slightly different version one. This one's a bit nicer to look at. And it establishes a metric on how we could measure if it's good or bad code, basically just by measuring how much the code reviewer curses about it. Now, the interesting thing about Clean Code is Clean Code never actually establishes any metrics, which is part of what I'm going to try to do in this code, to establish some metrics, which we can use to evaluate whether it achieves the goals it sets out to achieve. Yeah. And I'm also going to qualify quickly who I am. I'm of the opinion it shouldn't matter that much because it should be the arguments that should be examined, not the person, but I should still motivate that. Quickly talk about what is Clean Code. I'm assuming most here are familiar with the topic. Quick question, who does actually do Clean Code? Okay, a few. But I'm assuming most are familiar with the concept, or otherwise you probably wouldn't be here. And I want to establish that I'm also not building a strawman argument and arguing against just my own distortion of the concept. And finally, we're going to go through an example of a function, refactor it into the clean variant, step by step. This will be a bit dry and quite a bit of code slides. I apologize for that, but I want to point out exactly how much of a pain it is, first of all, to get it to be clean. And then we're going to test it under a refactor. What happens? How does the code change if we actually refactor it? Does it actually do it? Does it actually make our lives easier? And that's about it. Afterwards, we can have a short Q&A. Quick. If anyone, I don't have a problem with answering questions also during the talk. So if you can just raise your hand, that's fine. Or scream at me if I ignore you. Right. So who am I? I'm a lead developer with Materna. I've been with Materna for 3.5 years. I've got 20 years of experience programming. Now, of course, not professionally. I don't I'm not 40 or 50, but I've started programming when I was like 12. So I've been exploring a lot of concepts. I've reading a lot of code. I've been programming basically every day since then. And what I'm currently working on is cloud-based applications, event-driven, real-time automation platform, which I can't talk more about because of NDAs. So what is Clean Code? And why do I talk about it? Clean Code is a book that Mr. Martin released in 2008, I believe. And it is a collection of practices that he collected and claims that we should be following to achieve good software. One interesting thing to point out, these are not his points. He didn't come up with them, which is completely okay. If we look at the Gang of Four book, for example, they didn't come up with the design patterns either. It's fine to collect concepts together and say we should be following them for these reasons. I'm pointing this out because it is important to mention that just because you follow some of the concepts described in the book doesn't mean you're doing clean code or that clean code works. You need to use it, look at it as a package. And also why I'm talking about it. I deal a lot with juniors, mid-level, and senior programmers, and quite often I get the question, is this code clean? Or in pair programming, I see them keep changing and refactoring the code. And when I ask them, well, why are you doing this? The answer is often, well, it's not clean. Why do you care? And it's usually, well, it's best practices. But if we actually talk about it, usually it always just comes back to the book and never to any evidence or metrics or any concrete points. It's just, we do it basically because we've been told to do it. And I find that very concerning. The book also starts out with this statement here, which I find very objectionable. Basically, writing clean code is what you must do in order to call yourself a professional, and there's no reasonable excuse for not doing anything less than your best. Now, this implies, obviously, that anyone who's not doing his specific version, that book's version of clean code, is not a professional, which is a brave statement because, for example, if we look at NASA, we know they don't follow these principles. They publish their coding principles. They're not allowed to use the new keyword, for example, because they don't program on the heap at all. Are they NASA engineers, not engineers, not professionals? I don't know. Games engineers, compilers, operating systems, embedded chips. It leaves the question of who's even a professional in this book's opinion. It's just kind of a flavor of the general stance behind clean code, and that is also being perpetuated. These are statements and sentiments you actually find online, which is why I'm also pointing that out. And we find rules in there like follow standard conventions. I don't think any one of us hugely disagrees with that sentiment, or that we should use descriptive names. We may very well disagree on what a descriptive name is, but we agree that the name should be descriptive, and so on. So there's a bunch of rules in there that aren't really important, aren't really interesting, though there are some rules that are more interesting. Specifically, and this is the point that I'm going to be addressing most, this prefer polymorphism over if, else, and switch statements, because that is one of the major reasons of complexity increases in systems when you actually follow this, along with the small functions. And the book describes a function to be too long if it has roughly more than 4 lines of code. I think most of us kind of agree that is a bit short for a function, but it has very interesting implications when a function is that short about what it does to the system. If I have time at the end, I will talk more about it. We'll find out. Then there's the single responsibility principle, SRP. That basically claims a thing, usually either a class or a function, should only do one thing or have one responsibility. Now, it's usually not easy to nail down what a responsibility even is. It's very vaguely defined. which makes it kind of a useless principle, because I can define the responsibility of the program to be to solve the problem of the program, and suddenly the main function is all I need. On the other hand, if I have a function that loads a user, processes an event, updates it, and then saves it to the database, is that multiple responsibilities? Is the update and verification a different responsibility? I don't know. I much rather like to talk about concepts, that functions and objects do concepts. And a concept isn't a clear single responsibility. We can say it's the concept of updating a user, which makes it much more graspable. Cool. Admittedly, it's equally vague, and you can also define the entire program to be the concept of the program, and then you end up in the same place. Try, don't repeat yourself. In general, not a bad principle. Basically, if we have multiple code places that do the exact same code lines, we should just abstract them away. Problem is this usually promotes very early abstraction, and with that also bad abstractions. Because if we abstract, like let's say we have repeated ourselves only 2 or 3 times, we may not have enough information about the abstraction we actually want or need. When we use some abstraction, build the entire application on top of that abstraction, and then we find out that was a bad abstraction. And that's going to hurt us severely, instead of just tolerating that the code is in there twice, in maybe the same function, for example, or shared between 2 functions. Of course, if you have the same piece of code in there 20 times or something, this is not maintainable anymore, because at any change in logic, you need to find all of them and change it. It just ends up with, well, thank you. Good, I'll be hanging around here now and every now and then, I guess, motivating my computer to stay on. I don't know why the slideshow doesn't keep it awake. Please turn on. Thank you. And another one is dependency inversion, basically that we should program against abstraction. That is not a new idea, that's been around forever, and all possible paradigms do it. It's also very popular in functional programming to program against abstractions. But these will play a role in the refactor that we're going to do at the end. So metrics. The thing that we're actually interested in is why do we need metrics? In order to decide if something works or doesn't work, we need to be able to measure something that interests us. If we can't measure anything after we did something to the system, then we might have as well have not done it. So, of course, obvious metric is how long did it take to even write the program in the first place? The upfront cost. Another metric, these are metrics I'm going to actually track. Another metric is the refactor time, as in how long does it take to change the system after we wrote it? That's the long-term cost, basically. How does it affect program performance? And the system complexity. System complexity, I'm going to abstract away kind of as a graph. It's difficult to quantify or qualify exactly how complex a system is. And the way I want to do it for the sake of this talk is to pick out the concepts in the program we wrote, which is going to be types, functions. I'm going to represent classes or combinations of features with boxes that surround multiples of them. And then connect them with edges, that is, X uses Y, or interacts with Y, or has knowledge of Y. And for function complexity, we could use a metric like cyclomatic complexity. I don't want to pick more. We could turn this into a complete science and iterate on this forever. But these are just the metric. These are just the parts of a metric I want to use for the sake of evaluating if it's complex or not. Basically, it's enough to look at the graph and say, yeah, that looks simple or not. Lines of code, not a good metric, but it does kind of imply how much does the code grow over time. What's the cost of overtime as well? Because as the number of lines of code work, that's more things to test, that's more code to maintain, and it might be also interesting to just see what the effect is. So, What's a strawman argument? A strawman argument is when you pick the argument of a person and then intentionally restate it in a dishonest way, or not necessarily dishonest, but in a different way, and then you argue against this argument. And the result of that argument, whatever conclusion you reach, you apply to the original argument, which is not the argument you argued against. And this is very confusing to say, because argument is just repeated way too many times. But the point is, I don't want to build a strawman. I want to argue against the original intent. So Uncle Bob or Mr. Martin has a, okay, I think I need to move it once, has a blog. And on the blog in 2021, why is this, sorry, where's my taskbar showing? Just give me a second. Better, because now I can actually read when this post was from, in 2021. And so this is still a position the author of Clean Code holds. He on this blog gets asked how he would refactor this function. It's both times the same function. And the question is basically, how would you write it? Would you choose version 1 or 2? And there was a third version, which I didn't bring up. And to which he responds quite correctly that if the entire point of the program is to do with mapping, just use one of them, probably this one, because that's the simplest one to look at. But he doesn't believe that this is the only point of it, and that is business logic, and that is going to be reused, specifically also with results, and then there's going to be more switches built on top of it, etc., and the switch is going to be repeated. So he proposes to refactor it. So basically, this outlines that a function of this style, it qualifies for the refactor attempt. And parameters of these functions are, it has an input string, integer, an output string, and the output string depends on some rules based on what the integer is. So the yeah, but it doesn't really change the complexity, and I'm fine with formatting code that makes it easier or nicer to read. But yeah, technically, yeah, and if you do the curly braces, then you add even more. But yeah, yeah. Well, no, it's the same number of code paths we have if we look at it actually, because we have well, we go into one if we have 3 paths through the upper one, because either we set gender to male or we set gender to female or gender to unknown. The return isn't a separate path. And the other one here has 3 return statements. So we have the same cyclomatic complexity. Yes. So the example I'm going to use, I'm sure most of us are familiar with FizzBuzz. The reason I'm picking is because most of us are familiar with it, so we don't need to think about what the program is supposed to do, and we can just focus on actually the refactor itself. So the properties of FizzBuzz is we also have an integer as an input, and we have a string as an output. And we have a bunch of rules. Specifically, if the input is divisible by 3 and 5, we return FizzBuzz. If it's divisible by 5, we return buzz, and by 3, it's going to be fizz. And in all other cases, it's just going to be the string representation of the input integer. And if we just directly write it down, it's not too complicated. We just wrote down the statements right as they are. We can simplify this a bit. And this is Java code. I'm aware I'm using snake case. I'm sorry if that annoys some people. But I grew up with Python and currently writing Rust a lot, so it's just the natural way I write code right now. In projects, when I use Java, I use the proper convention, because the teammates don't like me otherwise. But We combined the 3 and 5 condition, because if it's divisible by 3 and 5 by inference through basic math, we know it's also divisible by 15, or has to be divisible by 15. And then it's just formatting. If you agree with it or not, I like it. So the way I'm going to capture performance is going through micro-benchmarking. Micro-benchmarking has a lot of issues, which we have to accept. First of all, it depends on the computer you're running it on. It depends on what the computer is doing when you're running it. It depends on the specific version of the JVM, because the JVM also has something called the just-in-time compilation, which does optimization of the code. So depending on which version of JVM you use or which compiler you use, you can get vastly different results, basically. That is something we need to just accept. And the way I run the benchmark is I'm going to measure in nanoseconds, and I'm going to average over 5 attempts. And I'm going to let it warm up 5 times so that the JIT actually had time to do whatever it wants to do. So this is trying to establish the best case scenario for this. And to prevent the compiler and JIT from optimizing things away, because it recognizes this function has no return value, and it's completely a pure thing that doesn't do any side effects, the compiler could have the idea, well, then just remove the function at all, completely, and don't have any code in here. And that wouldn't be a useful benchmark. We'd be just measuring nothing. So that's this black hole thing. It just prevents the compiler from making this decision. And this input state here has the same effect. It prevents the compiler from optimizing away the input number and trying to inline it and increase performance of the application that way. That's why there's this setup. But basically, all we need to care about is the inside part of it. And I hit a wrong button. Interesting. Okay, that button takes the screen away. So if we take a look at it, it took me 3 minutes to write. The runtime is about 25 nanoseconds per operation and 8 lines of code. I'm counting every line of code, not just the lines of code that actually do something, because if we look at it, technically we could say that's just 4 lines, or 5 lines if we could take the function signature into account. And if we represent it as a graph, it's super simple. We have an int that goes in, we have a string that goes out, and cyclomatic complexity is 4, because we have 4 paths through this function. 4 returns, spindle ifs. So what do we do to clean this up? These are, again, the things I want to mention, and I apparently forgot level of abstraction on the slide before. So let me shortly explain what that is. There's a concept of a level of abstractness of a function call in the book. And it's not very well defined what that is. I think we can all agree that low-level code is direct system calls. And high-level code could be right at the API layer somewhere. Like this is as high as you can go in your application. But which code is higher or lower, anywhere in between? How do we measure it? Do we just take the call stack and count how many functions it goes down? I don't know. And he doesn't explain. So I'm left to guessing. And I'm just, yeah, whatever. And the explanation for the original argument, just his suggestion of what to do with the male-female example, is that we should place the if-else case in a factory object that creates a polymorphic object for each variant, and then create that factory and inject it basically into the program, right? And the reason he wants to do it, because a switch statement is something he calls a dependency magnet, because apparently it's a bad thing if your high-level code depends on the low-level code that it uses. I'm not entirely certain why it's a bad thing, because any high-level code has, by definition, to use the low-level code for the application to work. One argument he brings is that the compilation time can increase through this, because if something changes in the switch, then the high-level code needs to recompile. Now, this is untrue with modern compiler that compile incrementally. they wouldn't recompile the high-level stuff if they see that just the function call down there gets changed. Because the address of the function call doesn't change necessarily, just the code it points to. And the other thing is a fear that if we have multiple switch statements in the application, that we will forget to modify it if we modify one of them, well, which would imply we have multiple switch statements that have the exact same body, which wouldn't make any sense if that's in a function, just call the same function. That's a different problem. Or that people would then instead switch over the results of it, which also makes, in my opinion, no sense at all, because the cases are determined by the input, not by the output. This is how he explains it in his blog. I can't explain exactly more what he means by that either, because this is all I have. And this is the kind of UML style diagram we get out of it. Basically, we have the high-level code pointing at the base class. That's the actual dependency. And then we have implementations we can inject somehow into the high-level code. So this is kind of what we're aiming for. And if we take a look at our original function, and this is the part where I just throw a bunch of code slides at you. We can, first of all, so the first thing we need to do is get rid of these branches here, because we need to get rid of the if-else statements. So the first thing we can do is to abstract away what it actually does with a interface, because if we look at it, it's the same shape. It's if some condition happens, then return some value. So we can just abstract it away with if this applies based on some integer, we return an optional string. Why do I return an optional string? Because I don't like null pointer exceptions. That's basically it. A rule may or may not apply, because if we look at the original implementation, we only return conditionally. So if we're going to check against multiple rules, then we need to have some method of saying this rule didn't apply, and we can encode this through an optional. We can then implement our rules. Nothing too surprising. It's just implementing it straight as it is. We have 3 of them. This is a candidate for try. We will take care of that. But for now, I'm just replacing the actual switch statement. Right? So we can just throw it in there. This is not injected. Obviously, it's all static. We'll do that in the next step. But the conversion can look like this one, where we just ask the rule if it applies, and if it applies, then we return the result. In our case, we return the X to string. Now, X to string is one of our original branches. It also needs to go. So let's do that next. We just create another interface for it and ignore the long, ugly names. I picked them because it's clearer what they are. And when I wrote that, it was 1 AM and I couldn't think of a name. And we can implement it straight up as just X to string, right? Oh, and another thing is level of abstractness, because X to string is clearly a system call-ish thing, whereas everything else is on the domain object of a rule. So if we, if we replace the default rule down there, we have as a static. That's all the changes we do, and then we can turn this into an object instance, inject our rules actually into there, and this is the FizzBuzz rule function we end up with. Now, there's a difference to what he said here, because the original was to return a polymorphic instance, as in we should return the rule to apply and not apply the rule. But the reason I chose this is because for the refactor later, this is going to be much easier, and we already have enough code slides. So the next simplification we can do is we need a factory. So I'm going to move the rules into a factory and then inject that factory into the FizzBuzz, which we get the rules out of. This is, again, part of a description of what the book actually suggests we do, which means we need to implement it. We just moved all the rules in here. And then just modify the constructor to use the factory instead. This supposedly has the advantage that we can use different implementations of this factory to yield different types of rules if we wanted to. If our program ever has that need, we don't know. But this is the code we end up with, right? Now we have try to take care of the 3 rules we just had, right? Perfect candidate for another factory. Why did you go back? So let's create a interface for what a rule is. It just takes the integer and returns a result, and that's what it does. And we finally implement the rule in a generic way, just returns the lambda. And then the factory just can return the make rule objects instead, and we got rid of all the implementations we had before, as well as the default rule just becomes a simple direct implementation. Now, if we look at the benchmarking code, I left all the annotations away because they're always going to be the same and they're not interesting. The way we use it is we inject the factory, in which we inject the factory for the rules, and then we apply the results to that. If we actually measure this, it took me 30 minutes to write, and I knew what I was doing and where I was going. Of course, there was some thinking involved, but this could be much longer in a time, especially when you're not entirely certain where to go. Performance here is 52 nanoseconds per operation if we use this new keyword here. And for those people that claim that the new keyword in Java is fast and doesn't have any costs, if we don't use it, we are 10 nanoseconds faster. So take from that what you want. But the reason I also measure it always without the new, that means I'm also injecting it through the state simply and construct it outside of a benchmark, is that one could then make the argument, well, the performance is just because you constantly construct it, and in a real application, you would just create this thing once and inject it in some runtime object, and that would use it. I don't want to fall into that trap. And we have 67 lines of code, which is about 60 more lines than we had with a simple example. And we didn't gain anything yet. Well, we gained one thing. We could make more rules easier, basically, instead of writing the... Actually, we don't have that either, because in the if-else chain, we could also just add another if-else in there. So actually, we didn't gain anything yet. Right, and the system complexity. If we look at the actual graph, then we have the factory that makes the rules. It has its interface, because we are doing dependency inversion. We have the FizzBuzz rule, which the make rule function obviously needs to know, because that's what it returns. We have the factory, the rules factory, and its implementation, because we're, again, going against the abstraction, which has the rules and the default rules, which both have cyclomatic complexity of 1, because they have no conditions in them. They, of course, need to know the FizzBuzz rule, and rules need to know the make rule. In addition, we have a default rule, which the default rule thing needs to know. Then we have our clean FizzBuzz thing itself, which needs to know about the FizzBuzz rule type. It needs to know about the default type. It needs to know about the factory itself. And then we can finally write our FizzBuzz function, whose cyclomatic complexity actually dropped to 3, which is a complexity reduction in that function. But otherwise, everything stayed the same. We can convince ourselves shortly that it's a cyclomatic complexity of 3, if I find it ever again. Yeah, we have a for condition, so we have 2 choices. We either enter the for if we have rules, or we never enter it. So that's number 2, and then we have an if here. That's cyclomatic complexity of 3. I should maybe generally just explain what cyclomatic complexity even is, and that is just how many code paths simplified through the code you have. And let me touch my computer before it turns off again. Okay, I need to be faster. Right, so what about a different implementation where we gain the same, let's say, benefits of the injection, right? because that's what he's after, that it's more dynamic and we have dependency injection and we're going to add a new rule later. So this makes sense to make now. I wouldn't do this at this point unless I knew in advance already that I have to add more rules, which no, but in one we had 0 dependencies, and in this example we have 1, 2, 3, 4, 5, I don't know, 7, 8, 9, something like that. A lot, more than 0. And I would argue this doesn't make the code easier to understand. And if I want, so for the maintainer, sorry, for the user, he sees both the interfaces here and he sees the implementation because he needs to call these. He doesn't see the other stuff here. That's okay. And the end user of FizzBuzz after the construction only sees the FizzBuzz, the original interface. But the maintainer of the code, he sees all of that and he has to deal with it. It's not just the end user we're talking about. We're also talking as a developer. And as a developer myself, this is what I actually care about, especially since I make a lot of architecture decisions. I hate this with a passion because I don't want to maintain this. Right, so I'm going to use TDD, and that is not the TDD you're thinking of. It's type-based, type-driven development, which is more a functional concept where you define your types first, and then from that, you go to your implementation. You don't write the tests. So the first thing we recognize are the type of a rule. It's just a pair of fields, a check number, and a string result. That's all it is. So let's also record it just as a field of data. The next thing we have is the default rule, which we're going to leave generic because the clean example made it as a injectable function, so we leave it as a function. We could just have it hard-coded in the actual function in the end, but I want to keep a parallel. I want to keep them as parallel as possible in their functionality. So finally, we arrive at a implementation where we inject the rules, the default rule, and then we input integer x. We have a very similar for loop where we just go through it, but except of its optional, additional optional, we can just return it if a check number passes the check. If a number passes the check, otherwise we return the default one. Now, this is a bit ugly, and we could carry this or create a functional factory for this because right now the problem is everyone that uses it needs to always know the rules and default rule, which can be a pain. So we can define FizzBuzz as a function itself, which just takes in an integer and returns a string. And then we can turn our original implementation in a factory now, which just takes in the rules as injected values and then returns a new function, which just operates on them. And that's actually our entire implementation. We didn't write any more code than that. The rest are just type definitions. The way we use it is we create our rules. They could come from anywhere, a file, a database, whatever. One could argue, okay, this should go into a factory, but sure, that would just be one additional type somewhere that the main function actually uses. The rest of the system doesn't use it. And then we call it the same way we called it before, just to see that we have the same interface in the end. How long did it take me? It took me 10 minutes, but I'm familiar with functional programming, so it might take someone who's less familiar with it longer. And it took me, and measuring it, also I wrote this first, so I was thinking here more, because the other one I wrote last afterwards. Runtime performance is 56 nanoseconds with new and 34 without new. This is faster than the other one, not by a significant margin. We can say this is roughly equivalent, especially in the context of micro benchmarks where we don't really know about ±5 anyway. Lines of codes, 22, significantly less. It's a third, basically. It's pretty much exactly a third. And if we look at the complexity of the system, we have the rules that only the factory knows about, which creates this function down there, and we have an implementation. And notice one thing, we have still this dependency inversion here. The thing that Mr. Martin cares so much about, we still have it in the system. So the thing he gains through his other system, we still gain here. Just the graph looks a lot simpler. And this seems a lot easier to maintain. It's straightforward. You know where to go if you want to modify how FizzBuzz works or how FizzBuzz is constructed. So let us introduce an additional rule. And that is rule faz. Some of us know that FizzBuzz has extensions. I think it's actually baz, not faz, but it doesn't matter. Basically, we can add more prime numbers, and if it's divisible by that prime number, it's this additional string, and then it's in combination to the others. So if it's divisible by 7 and 5, it becomes buzzfaz, and if it's divisible by 7 and 3, it becomes fizzfaz, and if it's divisible by all 3, it becomes fizzbuzzfaz. We see this as exponential, and it's exponential because a rule either applies or it doesn't, so we have two states, so it's 2 to the power of number of rules. And if we actually want to refactor our stuff, we look at the if-else, and we get kind of sad because we don't want to do that past 4 or 5 rules, because at some point of time we have hundreds of rules just listed, and it becomes an actual nightmare. So we want a more generic approach, which is also why I wrote it more generically in the first place, the simple variant. So what do we need for the simple variant? Well, we want to do string building now. So we are introducing a string buffer. And instead of returning, we append to the string buffer. And in the end, we return the either the default rule if a string buffer is empty. Otherwise, we're going to return the content of a string buffer. That is 4 changes, all localized to a single function. And at this point, we're done. We are already done. Well, we need to reorder our rules because the order matters now in the way we are appending it. The order just flipped. And it's instead of FizzBuzz or something, instead of the combinations, it's just the primitives themselves. So it took me 2 minutes. Measured, it takes longer, but we need to remember we're doing string building now. These are expensive operations technically. So it's not that much worse. It's okay. Lines of code are 2 more lines, which isn't bad. And the complexity of our system increased by exactly 1 type. All we did is we introduced the concept of a string buffer into the factory, or we introduced the concept of a string buffer into the FizzBuzz implementation, depending on how you see it. Maybe we added it to both. We could say that as well. But in general, the system didn't change much, which for me is a good signal that a system is robust and easy to modify and maintain. Now, what do we do with the clean variant? Well, first of all, it took me, I actually had to sit down and think about where do I even start? Because I could start in the factory, I could start in the rules factory, so in the factory that creates the rules, or in the factory that creates a single rule, or I could start in the actual implementation of the code that uses those factories. I chose in the end to implement it directly in the function that uses it. The change is rather similar, but we notice something we don't like as clean coders, and that is buffer to string is definitely a low-level code abstraction, whereas rule apply is not. So it definitely isn't allowed to stay in there. Same as this buffer append here. We don't want it here. So we need to move this buffer append somehow into the rule itself. And I keep pressing this button because it's so nice. So let's change our interfaces actually. And the default rule and the actual rule just get the string buffer passed in, which they then modify. So we shove it deeper into the code basically. When the implementation doesn't change much, we gain the buffer here and we do buffer append. We lose the optional now because if it doesn't apply, we just don't touch the buffer. FizzBuzz then just shoves the buffer in the rule, but we still have this pesky buffer to string in this new buffer up there, which we also want to get rid of. And how much time do I have? Okay. So we then create this thing, and this is where I ran out of patience and just coded it all down. And didn't go through it step by step. Basically, I'm going to motivate why I did this here in a second with the exact code example we have in the book itself. What the book suggests is that we sync the buffer into an instance variable, and that this instance variable is then used by the rest of the application. And this is inside of an internal private class that does it, because that is the responsibility of that thing. And then because we want to maintain the single responsibility principle and the small functions, we have then apply rules to X and then return the results. And then we just have them here, just move to here, right? And then our original implementation of this was just turns into creating this new runner and then calling it on it. This is the example in the book. Just to motivate it, he created a setup teardown includer that is this internal thing. And you see that he has a static function here which calls this thing and then calls the render on it and passes the thing in, and then the thing is just built of a bunch of private methods. Which are all in the style of just 3-4 lines of code. And here we have the actual separation. So for him, buffer in his example is also a low-level code, which is why he pushed it into this one line down here, whereas in everything else, it's just calling this include. So the refactor time took me 15 minutes. The performance plummeted to an amazing 138 because of the inner thing and the small functions. And without the new, we still have a amazing performance of 130 nanoseconds per operation. And our line of code drew actually to 82, which is we went from 67. So 11 lines of code? Can I count? No, I can't count. I don't know, 13, something. It's more than 2. If we look at our new graph now, I'm not sure I would call this particularly clear or easy to understand code. So let's see, we gained the string buffer up there. That's the same cost in the other system. We have this internal instance buffer that everything uses. Now we return the value from this inside thing, which has a bunch of internal functions that uncontrollably read this buffer. And the reason we need this as an instance is threading. Because if we move this buffer into as an instance variable of this thing, if we call this thing twice in a row from different threads, let's say this is an API, web API, and we call it with multiple threads through the API, then this thing would possibly be called at the same time. So when things write to this buffer, they could be writing to it at the same time, and that would be catastrophic, and a bug that is very hard to find. Anyone that worked with concurrency knows that bugs where you write in the same buffer in parallel are pretty much impossible to find, or at least after you need a cooldown phase afterwards, because yeah. So this is why it's in an internal class. This scopes it. Yeah, I'm not gonna say much more to it. I think it's self-explanatory, but this is not what I want as a system maintainer. Well, it is according to him. That is according to the book. This is literally according to the book. I know that most people that actually really like clean code will tell me this is not clean code. My goal is not to convince you. My goal is to either entertain those that don't like clean code or motivate those that are on the fence to think about it, to evaluate it again. And if you arrive at the conclusion that this was a misrepresentation, that's okay. Or if you arrive at the conclusion you want to still do it anyway, that's okay. Perfectly fine. And in some contexts, clean code might be the right answer. But in the general case, and it tries to be a general purpose case, I don't think it's the right answer. Right, so here's a summary slide. And I think I went through this a bit faster than I thought. Basically, creation time takes much longer. in any case, which could be fine if the maintenance time goes down, but the maintenance time also went up. And it's way more complex, and the benchmarks all went up. And I know there's a bunch of people that say performance doesn't matter that much. It does. It really does. Try playing a game where your frames drop from 60 to 30 or lower, and you know performance matters. And the argument that you can just add more CPUs doesn't work when you're working with a web front end, or if you're working on a mobile phone, or if you have to pay for those CPUs and you don't want to pay for the extra CPUs, because any extra resources we assign are resources we have to pay, and these are long-term resources we need to pay. We need to pay them every day. And this is just the reality, especially in the context of our climate problem right now. Performance is very much something we need to care. Just adding more power is not the answer. If we can avoid the problem much easier by just not artificially hiking the performance up. Does that mean we need to sacrifice everything possible for performance? No, of course not. There's nothing wrong with dropping a bit of performance here and there for better architecture, for better maintenance, etc. But the point I just want to make is don't overdo it. Right. At this point, we have time for questions. And yeah. Do we have questions? No. Good. Other opinions? Statements someone wants to make, maybe? Yeah. So the reason I'm thinking about it that way is because I'm thinking about what do I have to have in my head to maintain this? What do I have to actually think about? And I need to think about all these like concepts when I actually maintain this. I don't need to only know that FizzBus exists. I need to know that it implicitly uses this buffer when I modify this function. I need to know that. Even if the book claims that functions with less arguments are easier to maintain and understand because, well, they have no arguments. So they're simple to understand, right? But as most people that know functional programming will tell you, functions have two sets of inputs and two sets of outputs. We have the argument list and we have the return type. And then we have the hidden inputs and the hidden outputs. And just because you move something from the argument list to the hidden inputs doesn't mean you made the function simpler by reducing the number of arguments. You just moved them to another list. You just hid them. But it's something that before was written explicitly there. If I used the function before and I had the argument string buffer, I knew about it. I knew it does something to the string buffer just by looking at the function. But when it's in the hidden argument list, I don't know this. I need to know this. I need to read the source code. This is implicit knowledge I need to have now. And that's also one of the huge problems with small functions. They add the amount of implicit knowledge I need to have. I need to know when are they called, by whom, why, what are their invariants, do they have any side effects, is it safe to call them? I don't know. I need to read all these small functions. And if I have 15 of them, instead of 3 functions, then I need to know 5 times as much about them. And as the system grows in complexity, and once we have like 500 functions, 600 functions, 1,000 functions, it becomes really difficult to keep in your head. Most people give up at 7 things to keep at the same time in their mind. At least people say that that's what people do. And it's roughly my experience as well, that I don't care after number 7. Right, good. Then I thank you for the attention and have a nice day.